Alright, last section for Chapter 2, 2.10, intersecting chords, secants and tangents. Now I'm going to do something a little bit controversial here. I'm going to call these, rather than two separate theorems, we're going to call these the power of a point and show that the one theorem can satisfy both equations here. The first one, where the point is inside the circle, like we have there, and the second one, where a point is external to the circle. And what we're going to show is that if PAB are in a straight line and PCD are in a straight line, then the product of PA multiplied by PB is equal to the product of PC multiplied by PD. And it doesn't matter which situation we're in, but there is a little problem with the way they've labelled their circle up there. I want P, A and B to be all in a straight line. So ideally, this one, I would have the chord AB, or the secant AB, and this chord I'm going to call CD. And you'll see why. It doesn't really change. The theorem is still these two sections are going to multiply and those two sections are going to multiply. But I want to use the one terminology to cover both situations, and it'll make your life easier. So we're going to go down here and have a little proof of why that must work. So let's get our circle with our intersecting tangents. So the point where they meet is P. Sorry, not tangents, these are chords. Now one of that P lies on the line AB, and the other chord that I have there is CD. Now let's see how I'm going to show that the product of that distance by the PA, PB by PA, is the same as PC by PD. Well, let's create a couple of triangles here. This is all about triangles, this one. Straight away we've got our bow tie, our butterfly rule, or our angles at the circumference rule if you'd rather. If it doesn't take too long, this angle at the top there must equal that angle at the top. These two angles in the middle are vertically opposite, and because they're in the same sector, I can have, let's just use a different colour, angle A down here is equal to angle D down there. So I've got two similar triangles. So let's see how we would write that ratio so that we'll do the one on the left, the triangle on the left, divided by the can compare it to the triangle on the right. So if I take the longer side from the dot to the blue side, I've got PA, and I'm going to divide that by PC. Now that ratio, because these triangles are similar, angle, 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 will be the same as, now I went from the dot to the blue, so I've got to go dot to the blue, PD divided by PB. And you say, well, hang on, that's not the rule you told me it was going to be. You told me it was going to be PA by PB equals PC by PD. Let's have a look and see why that will be the case. Well, let's just multiply through by a common denominator. I don't like those denominators. So I'm going to multiply everything by PC and PB. That means on the left-hand side, PCs will cancel and I'll get PA multiplied by PB. And on the right-hand side, the PBs will cancel. I'll have PC multiplied by PD. Hey, we got what we wanted. So for a point inside the circle, we've proved that it works. What about for a point external to the circle? There's my point P. Now remember to make P, A and B collinear. Collinear, you'll remember, means lie on the same line. And P, C and D are also collinear. Now, how am I going to construct this to show that they're equal? Well, a little bit of creative play here gets me a cyclic quadrilateral. What do I know about cyclic quadrilateral? Their opposite angles are supplementary. So that angle there, if I can put a dot in there, and this angle over here at D are supplementary. But in addition to that angle D, we know that angles in a straight line are supplementary, and you can see here I've marked in the other angle that would be supplementary. So we've got two angles that are equal there. Could I use this information at all? Well, I could use the same theory to find out that this angle here at B, I'm just going to colour it blue, must be the same as that angle there by the same scenario. Opposite angles in a cyclic quadrilateral are supplementary, and therefore PCA is going to be the same as PBD. I've got similar triangles, angle, angle, angle. Let's write our rule. We will do the small triangle over the large triangle. So I'm going from P to the red angle first. So PA divided by PD. And then let's go to the blue ones. And I'm doing small on top. So PC, that would be equal to PC divided by PB. We are not interested in those denominators. They're ugly, they're annoying. Let's multiply through by a common denominator. So I'm going to multiply by PB and by PD. Let's see what we end up with. I think you're going to find that we get PA by PB on the left. And on the right, I've got PC multiplied by PD. So regardless of which way you have it, if the point's inside or outside, if you have a point and a line forming a secant to a circle or a chord, depending on whether the point's inside or outside, the product of the lengths will be equal. We better find an example and make sure we know that this works. So I've just drawn out question 5 here from the final exercise. Now let's see how I would use this rule. Well, here's my point P. If I can get my labels working again. There's P. I'm going to call this one A and B because they're in a straight line. And so these points will be C and D. Now my rule, PA by PB is the same as PC multiplied by PD. It's important you get these right. So PA is 9 meters. Multiplied by PB, well PB is 9 plus 14, so that's 23. And that would be the same as PC, which is 8, multiplied by PD is 8 plus X. You can see that I've got to get the whole distance there. Now we can go ahead and do it. 180 plus 27, that's 207. Equals 64 plus 8x. Let's subtract 64 from each side. And I'm going to get, what's that? 143 equals 8x. Final step, divide each side by 8. And 143 over 8. Oh, the 1 didn't work the first time. 143 over 8 equals x. And our units are meters. So we put meters in and we're done. Alright, I got a little carried away. I was going to stop, but I want to do one more. Whoop, don't scroll it out of the way. This is 8F, one where the point is inside the circle. Now you'll see there I've been careful to label A and B so they're in a straight line, and C and D so they're in a straight line. That way I can apply my rule, power of a point. PA multiplied by PB is going to be the same as PC multiplied by PD. PA and PB are easy enough. That's 5 by 13. PC and PD are each x plus 1. That's not too bad. I've got 65 over here. On the left hand side I get x squared plus 2x plus 1. Subtract 65 from each side. Because whenever you're solving a quadratic, you want to ensure that you have all of your values on one side, set it equal to 0 and use your null factor law. So I've got x squared plus 2x minus 64 there. So we're now looking for factors of negative 64 that add to equal 2. I think we're going to struggle here because 64 is just a power of 2. So what do we got? We've got 2 and 32, 4 and 16, 8 and 8. It's not going to look pretty. So we could use our quadratic formula, or we could use our favourite rule in maths by being a bit sneaky way back up here. You can see that I've got 5 by 13 equals x plus 1 times x plus 1. I could write 65 equals x plus 1 all squared. Now I did say you've got to set them equal to 0 and factorise, so let's do that. But now look at that, beautiful, your favourite rule in maths has appeared. The difference of two squares, x plus 1 squared minus root, I'm pretty sure that's 6 then 5, root 65 squared. Favourite rule in maths, a plus b, a minus b, so it's x plus 1 plus root 65 and x plus 1 minus root 65. they multiply to equal 0. Therefore, either the first bracket equals 0, null factor law, x plus 1 plus root 65 equals 0. That's going to give me x equals -1 minus root 65. Well, hang on, that can't be right, because that's going to be a negative value for x, and it's going to make that distance less than 1. So we can reject the negative value. But the other one's probably going to look after us just fine. Let's have a look here. X plus 1 minus root 65 equals 0. So I would add root 65 and then subtract 1. X equals root 65 minus 1. There you have it. Alright, enjoy the rest of the exercise.